So we're going to be taking a look at the Chapter 8 guide for stats. This is on the hypothesis testing for mean, proportion, and deviation. We're going to start with some of the basics of p-values and stuff. So the first question here says find the p-value if the test stat is 0.23 and it's a z-score. So we're going to be using our z-table. And it also says that the test is left, right, and two-tailed. So we need three values here. So a left tail test for z-score is pretty easy. All you do is you go up to your table, you find this z-score on the side and on the top, and figure out where the lines cross. So let's pull up a z-score table here real quick. There we go. And it's 0.23, so let's zoom in on here. So 0.23, here's 0.2. We look for 0.03, there that is. So we find out where these two cross, which seems to be about right there. So 0.5910 seems to be about where our score is. So we'll go ahead and put that down. 0.5910. Now, if it was a right tail test instead, what we would do is we would take that 0.5910 and we'd subtract it from 1. And in this case, that would end up giving us 0.409. Again, the reason we subtract from 1 is because the z-scores are assumed as a left side test. So when you get 0.5910, that means that if you had the curve, so here's our Humpty Dumpty graph there, your z-scores right here, it means to the left of it is a chance of 0.5910. So if you want a right tail test, you have to take this and subtract it from 1 to get the other side of the z-score essentially. And then for a two-tail test, you have to kind of think a little bit. For a two-tail test, if your z-score is positive, what you want to do is treat it like a right tail test at first. So 0.5910, subtract it from 1, you get 0.409, put 4 there. So once you get 0.409, then what you're going to do is, because it's a two-tailed test, you're going to times it by 2. Because this 0.409, if I draw again another little Humpty Dumpty graph here, there we go. It means that, this is the positive z-score. Over here is 0.409 worth of area. And then the negative z-score, its negative counterpart, is also 0.409 area. So together, with those two tails, we're going to times them by 2, or double it, and we get 0.818 worth of area. So this was just kind of testing all three types of possible tests you might have when you're changing your p-value, or when you're changing your test stat to a p-value. Left tail, again, look it up and leave it. Right tail, look it up and minus it from 1. And then for a two-tail, if it's a positive z-score, you look it up, minus it from 1, and then double it. If it was a negative z-score, you would just take it and double it. Again, a negative z-score for a two-tail is treated like a left tail twice. A negative z-score for, or positive z-score for a two-tail is treated like a right tail twice. So let's go ahead and go to the next one here, which is writing the alternative and null hypotheses. So we have the average number of students in a class is less than 30. We want to put that into HO and H1 form. So if we're going to write this down, we're going to start with our HO. So HO. And that's going to be, since we're dealing with average is a mu symbol. Okay, so average is represented by mu. So we're going to say mu is equal to 30, because your null hypothesis should always have an equality in there as standard for what we're doing. So your null hypothesis is always going to be mu equal to, p equal to, or sigma equal to. Remember, mu is for average, p is for percents, and sigma is for standard deviation. So p you use for percents, sigma you use standard deviation, and then mu you use for average. And then our h1 would be mu. In this case, we're testing that's less than 30, so it'd be less than 30. And those would be my two hypotheses. So because it's a less than, this would be a left tail test if I were to go any further. So that'd be kind of how I would proceed from there. But in terms of writing the hypotheses down, this is all I have to do. Number 3 is, again, not a full hypothesis test. It's just asking us to find the test stat. So it doesn't want us to do the complete test, just find the test stat based on this information. So let's go ahead and write down the information that we're going to need. So for the test stat for a z-score, there's a formula sheet in the back of the study guide, but if you don't know, it's z equals p hat minus p all over root pq over n. Kind of a long formula, but You use it enough, you memorize it. So we need to figure out all of these pieces here from this word problem. So we need to figure out our p hat, our p, our q, and our n. So let's go ahead and see if we can't find those out. So a study finds out of 400 employees. So that's our n, 400 employees. 8% of them said that they have stolen money. Find the test stat for the claim that more than 5% at the company has stolen money. Okay, so 8% of them have stolen money. So that means that that's the sample percentage. That's what we got from the 400 we asked. So 0.08 would be my sample percentage, my p hat. I'm claiming that's no more than 5%. So that'd be right here, 0.05, because that's my claim percentage. P no hat, remember, is what you're claiming. Then Q, by converse, would have to be the opposite, which would be 0.95, or not the opposite, but the complement. So again, Q is 1 minus P. That's how we get Q. So 1 minus whatever this is. So we have our P hat, we have our P, we have our Q, we have our N. So sample percentage, claimed percentage, 1 minus our claimed percentage, and our total number of people surveyed, or total number of things tested. We're just going to go straight and plug it into our z-score. So our p hat is going to be 0.08 minus 0.05 for p no hat, all over big root 0.05 times 0.95 all over 400. Again, very big formula. Type it out in pieces if you need to on your calculator, but in the end you should get about 2.75. It doesn't tell us to ask. It doesn't ask for a p-value, so we can actually just keep it as a z-score. If it asked us to change it to a p-value, we'd look up in a table and get our p-value from there, and we'd have to figure out our hypotheses because we'd have to know whether it's a left or a right tail. But if it just asks for the test stat, this is what you do. And in fact, this is how you start any hypothesis test problem: is you find the test statistic using the information they give you. This was for a z-score test stat. For other test stats, we have different items that we look for. But that's how you start every problem: is plug in the formula and get your z-score, your t-score, your chi-score, whatever score you're doing there. You want to get that first, and then you can proceed to figure out the other one to compare it to. So the first three were just kind of bits and pieces of the problem. Let's look at one that will take the problem from start to finish here. All right? So, excuse me, this one says identify the null and alternative hypotheses, t-stat, critical value, p-value, and state a conclusion. So basically analyze this data. So again, give us supports, doesn't support, reject, failed to reject. It just wants everything done. So let's go ahead and look and see what we're going to do. 1,200 cell phones tested. That's probably important information there. 638 were purchased by teens. 0.04 significance test, which is a little bit different than normal, but we can handle it. More than 50% is the claim. All right, well, let's get all our information down first. So we need a p hat, we need a p, we need a q, we need an n, and then because we're going to do this all the way through, we're going to need an alpha to get our significance level. Okay. All right, so let's see what's going on here. So p hat, well, they don't give us it directly, but we know that it's 638 out of 1,200 were purchased by teens. So if I wanted to write that down as a percentage, I would just do that fraction, 638 out of 1,200. That would be my p hat. That's the percent of teens that purchase cell phones. My p, my claimed percentage, is just 0.5, my basically 50%, because that's what I'm going to test against. I'm going to test it against 50, whether it's more or less than 50. So it's my claimed percentage. That means q also is 0.5 because remember it's just 1 minus p, so it has to be the other half. N, we have 1,200 people using the cell phone, so that'd be 1,200 there. And then alpha in this case is kind of a rare significance level of 0.04, which is not standard, but again, workable. And then we need to write down our hypotheses, because if we're going to do this all the way, we need our hypotheses written down so we know how to compare our numbers at the end. So in this case, I'm doing a percent test, that's why I have the p's over here. So my null hypothesis is that it's equal to 50%. And then my alternative is that it's more than, almost put less than there, more than 50%. And this is my claim, so I'll put a little note here that says this is my claim. I'll put a C there, so I know it's my claim. And because it's greater than, I know it's going to be a right tail, which is going to help when I'm deciding my p-value. Okay? So that's step one, essentially. So if I'm trying to break this up into steps here, that's step one. Get your information, get your hypotheses down, set. Right? Again, claim percentage, sample percentage, 1 minus the claimed percentage, number of people surveyed or number of things tested, and then the significance level that they will tell you. So my second step, after I get my information down, you can kind of consider this part of the first step too, depending on how big you want to make your steps, but is to get my test stat, get my z-score. So that's when I use that formula we had before. That's the p hat minus p over pq over n rooted stuff. So it'd be 638 over 1200 minus p, which is 0.5, over, and then we have that big square root. Then we have p, we have q, and then we have a big 1200 there. Okay. And if you solve this out, you end up getting 2.19 as your test stat. Okay. So this is my z-score. Let me try that again. I'm trying to have trouble running here. I'll try to type it out, just hopefully it doesn't go too much there. So this is my z-score, also known as my test stat. Okay? Both of them mean the same thing. A test stat is just something that you can compare with. So next spot or next stage, we have our information down, we have our test stat solved. Now we need to find our p-value. Because it's a z-score kind of test, we want to change this z-score into a p-value. Again, the reason being is because we're going to compare the chance of getting this z-score with our threshold, which is this chance right here, the significance level, and see which one's higher. Because the significance level is given as a probability. 0.04 means 4%. Basically what this means is that your cutoff is 4%. If you're less likely to happen than 4%, so 3%, 2%, 1% chance of happening, if you're less than 4% likely chance of happening, then you're probably cause for significant concern. So that means that something is happening here that we want to take note of. If you're more likely to happen than 4%, so 5% on up, then we really don't care about it. Then we're just going to say the null hypothesis is not proven, but the null hypothesis is supported, so therefore H1 is not supported. So let's go ahead and change this z-score, 2.19, into a p-value. So to do that, that's where we're going to go to our friend the table, and we're going to make sure that we remember it's a right tail test. So let's look at the table first. So 2.19, let's remember that. All right, so 2.1 was be right there. And then 9 would be all the way at the end. So let's take this column all the way down, 2.19, right there. So 0.9857. So let's write that down in our little chart here. 0.9, whoops, 9, 857. Now normally we would stick with that. Unfortunately, it's a right tail test. So what we have to do is take that and minus it from 1. So 0.9857, subtract that from 1, and you're going to get 0.0143. Right. Step 3. So this is our p-value, our PV, my p-value. Now, it says up here to also find the critical value, which you actually really don't need if you're doing a z-score test. The critical value is usually used for t-score or chi-squared tests, but just for completeness sakes, I'll do it here real quick, but know that you don't necessarily have to do this. So we'll call this step 3B, because this is an alternative step that you could do for like t-scores and chi-square scores. You can do it for z-scores as well, obviously. It's just not really common. So again, this is kind of an extra step that you don't necessarily have to do on a test, because you'll have a choice of what style to do it in. So to find your critical value, what you do is you take your alpha, which is 0.04. That's my alpha. That's this one right here. Because it's the right tail test, you kind of do the same thing you did over here. You take 1 minus it, and you turn that into 0.94. This is basically kind of like a temporary p-value. So you're going to take this 0.94, and you're going to look up what z-score goes with it. So 0.94, let's remember that real quick. We're going to go to our table. We're going to try to find 0.94 in this mess here in the middle. So we're going to try to get as close to 0.94 as we can. And I believe the closest I can see for 0.94, let's see here, would be here's 0.945, 0.941, 0.9406, 0.9394. So if I have 0.94, which if I go check back here, I actually made a mistake. My bad. 0.04, 1 minus 0.04 is going to be 0.96. But I caught that before, but I've done the wrong number. So I'm human too. I do make errors every now and then. So my bad here. Let's go to 0.96 instead. A slight calculation error. 0.96, 0.96, 0.96. There it is. 0.959999 is about as close to 0.96 as we're going to get, I think. That's pretty darn close. So that's going to be, so this is my p-value. I want to look at what z-score makes that. So over here, 1.7. Up here, 0.05. So in total, we have 1.75 as my critical value. Again, that's just what I got from the table there. 1.7 on this end, and then 0.05 on that end are what make that 0.9599 number. So if I was doing a t-test, what I would do is I would take this critical value and compare it to my test stat and see which one's bigger, which one's less, and then what that means in terms of my interpretation. But usually for a z-score test, you don't necessarily need the critical value. You can use the p-value you got over here, and then use that, use that to compare. So my fourth step is to do just that, is to compare. So I always compare my p-value to my alpha with a z-score test. So my p-value was 0.0143. My alpha is 0.04. I need to figure out which one's bigger. Well, think about them as percents. 4% is a lot bigger than 1.4%. So right there, alpha wins. So p-value is very small, which means that this whole situation has a very low chance of happening by chance, by circumstance, just by happenstance. So that means that what we do here is we reject, let me write this out with typing here because my handwriting is going to get really messy. So let's try this out here. So since p-value is so low, we reject, again, reject HO. Let me see if I can get a subscript here. That's a superscript. Let me try that again. There we go. We reject HO because p-value is so rare a chance to happen, it's probably not happening by chance. Because remember, HO is basically assuming nothing is going on, assuming everything is functioning normally, all the variations are in their bounds, nothing out of the ordinary is happening. Well, clearly something out of the ordinary is happening because this thing happened and there's only a 1% chance of it happening by circumstance, a 1.4% chance of it happening just by random occurrence. So something's probably influencing this here. So we reject the null hypothesis, we reject the status quo, and then that means that since our claim, remember, rejecting or not rejecting HO does not say anything about your claim. That's just a matter of rejecting or not rejecting HO. For your claim, you need to figure out, okay, would this support or not support my claim? Well, if my claim was H1, HO got rejected, which means H1 got supported. If I support H1, that means in this case I also support my claim because my claim was H1. So in this case, I would say that the data here, there you go, the data supports the claim. Okay? And if you want to, you can say the claim that more than 50% of cell phones are purchased by teens, because that's the actual claim in words there. But if you just say data supports the claim, then we're good. So again, usually if you reject the null hypothesis, your data is going to support your claim because most of the time you claim the alternative, you claim H1. If it's a two-tailed test and you're claiming not equal to, then that might not be as true. But if it's a left tail or a right tail and you reject HO, you're probably supporting your claim. So that's a full run through for a z-score problem. We have a few more coming up here that aren't z-scores. We have one t-score and one chi-square test as well that we'll get to. But this is kind of form the basis, like the first second step are the same in almost all the problems there, and the comparison on number 4 is very similar to all the problems. So really the only changes are in step 3 and 3b. These get changed around a little bit when you go to different testing, but step 1, 2, and 4 are pretty consistent. Let's look at this one here. Speaking of changes. So it says find the test stat, which is a z-score they're telling us. If n is 50, x bar is 580, mu is 630, and the standard deviation is 45.8. So in this case here, since we're dealing with an average and an x bar, we're going to use the mu formula for the test stat. So the average formula for the test stat using a z-score is x bar minus mu over sigma over root n. Again, it's a formula in the back of the study guide. You'll have that for the test as well, so you don't need to memorize it. But your key notations here are x bar, mu, sigma, sigma. So if you don't know what formula to use the one that matches the numbers of the variables that you're given. So in this case here, we have 580 minus 630 over 45.8 over root 50. And then we plug that in, and we end up getting negative 7.72, and that's all we have to do. It doesn't ask for a p-value or a critical value, so that's it. And this is just a simple plug and chug problem. Find your formula, take your variables, plug in the numbers, chug out an answer. That's it. Just, again, use the variables themselves to figure out what formula you should plug them in for. So if that was if this was a S and this was a sigma and I didn't have this one here, I might be using a different formula. Or if I had a P and a P hat, I'll be using the P hat formula I did in the last problem. So just look at the variables so you know what formula to use. All right, let's go to number 6 here. Again, this entire sentence here just basically means make a conclusion from this setup here. Again, it says find the critical and the p-values. We only really need to find one or the other to make our comparison, so we might stick with that instead. So we're testing the temperatures. Let's see here. They are found to have a mean of 30.37. So mean is a tricky little word there. Mean has two possible formulas. One is a z-score, one is a t-score. If you have a mean and you're going to use the z-score formula, that means you have the standard deviation of the entire Florida Everglades, of your entire population. So if we're testing the Florida Everglades, that's my population. If I know the standard deviation for temperatures of that entire region, then I have a z-score problem. If I don't, and I just test the mean of the portion of that area that I tested, that's called the sample deviation, then I have to use a t-score, which accounts for more variation from the fact that you don't have the entire deviation yourself. So let's keep reading on here and see what we have here. Out of the 61 temperatures on the 61 different days, so that's the mean of that, of 61 temperatures in 61 days. Assuming that the standard deviation is 1.7, test the claim that the mean is greater than that using a significance level of 0.05. Okay, so they don't necessarily say standard or population. If they don't say sample deviation, though, you can assume it's the population deviation. It says assuming that the standard deviation is 1.7 degrees Celsius. So if it doesn't specifically say that this is just from the sample, you can assume that that standard deviation is for everything in the population. So this is going to be a z-score kind of mean problem, because again, the key thing here is that we don't have a sample deviation, we have the entire standard deviation of the entire population, not just of the sample that they're picking. So to do that, again, your formula's in the back of the study guide. We're going to be using the z-score formula for a mean, which requires us to use x bar. It's the formula we just used, actually. X bar, mu, and sigma, or actually sigma and mu, I got those backwards. And then as always, our alpha and our n. So we need to get these numbers from my word problem. So x bar is my sample average, and it says here my sample average is 30.377. So 30.377, that's the average of the temperatures that I got from my sampling. 61 temperatures in 61 days. Now, it's written twice, but it's not 122. It's just 61 as my n, because I had 61 temperatures that I'm looking at. So I don't need to add the two 61s together. It's just take one of them. Standard deviation is 1.7. Okay, so standard deviation, that's sigma, is 1.7. And our claimed average is 30 degrees Celsius, sorry. So that's my claimed average, 30 degrees Celsius. And my significance level, my alpha is 0.05. So again, significance level means alpha. Significance level, alpha. All right, so that's step 1, got all my numbers listed. Step 2 is to use the formula. So in this case, we're going to be using the following formula that we just used in the past problem. X bar minus mu over sigma over root n. So we just go to our number list here and plug in those values. So 30.377 minus 30 all over 1.7 over root 61. Plug that into your calculator, and you get a test stat of 1.73. So that's, again, my test stat, the first thing I find in all my hypothesis testing. Box that in there. That's my test stat, 1.73. Next thing I need to find is my p-value. We won't bother finding the critical value because we really don't need to in this case. So we'll find my p-value instead. Because it's a z-score formula, and for z-score formulas or for z-score problems, you take your test stat and change it into a p-value so you can compare it to the alpha. Because again, your ultimate goal is to compare to this. Sometimes you might need to change this into a different score, like a t-score or a chi-score. But for z-scores, you can just change your test stat into a p-value instead. So what I'm going to do is I'm going to take 1.73. That's the test stat. I'm going to look that up in my table and figure out what p-value comes with that. So 1.73, 1.7, 1.70, 1.71, 1.72, 1.73. So 0.9582. Let's go to that. 0.9582. Then I need to see if it's a right or left tail. And one thing I forgot to do that I probably should have is write down my hypotheses. So let me do that over here, because my hypotheses tell me what kind of tail test I'm doing and whether I need to do anything with this. Given that it's about a 95% area, I probably am going to have to subtract from 1, but let's just see. So my mu is set equal to, I'm testing against 30, right? That's the claim that I'm making. Claim is that the mean is greater than 30. So I'm going to assume it's equal to 30 and then hypothesize that's greater than 30. So this is my claim, my little c there for claim. And because it's greater than, that means I have a right tail test. This is an R tail, so we'll put R tail because you're testing a greater than claim. So let's go ahead and take this and subtract it from 1, 0.9582, because in a right tail test, you take your p-value and subtract it from 1. If this was a left tail test, like I was testing if mu was less than 30, then I would just leave it. But it's a right tail test, so I have to subtract it from 1, like I did the very first problem, and I get 0.0418 as my true p-value. So now I have that down. Last step is now to compare. So I'm at the comparison step here. Let me write that a little bit better. There we go. So step 4 is to compare. So again, you compare your p-value to your alpha. Well, my p-value is 0.0418. My alpha is 0.05. It's pretty clear that 0.05 is bigger than 0.418. So my alpha wins, my p-value loses. Or instead of saying loses, put another way, your p-value is a really, really, really small chance of happening compared to what your threshold is. Okay, so if that's the case and the p-value is very small, whoops, wrong one, there you go. That means that we are going to reject HO, so reject HO. I keep doing the wrong one, HO. And since we rejected HO, the data is going to support our claim, because our claim, remember, our claim was H1. So the data rejected HO, it supported H1, therefore we reject HO and support our claim. Again, if P is low, the null must go. That's kind of the rhyme that goes with it. If P is low, null has to go. And remember, HO represents the null. So if P is low, null has to go, and then you can check to see whether that supports or does not support your claim. All right, so let's do a few more minor ones here before we do another big one. So this is a t-table test we're doing here. T-table, if you don't remember, looks something like this. Okay. So if you notice here that it already gives us what kind of areas to use. So this is area 1 tail, this is area and 2 tails. So I don't have to worry about dividing by 2 or anything like that. It kind of does that for me. You also notice that they're all positive, and because it's symmetric, that means I can look up the positive value and just switch it to negative later. Like for instance, if I want to look up 1.5, I would try to find, if I want to look up negative 1.5, I would try to find positive 1.5 in this table, look up that value, and then go with that, because the positive values are going to be the same as the negative values, just on the other end. So it doesn't have any negative numbers, so if you do have a negative number, just switch it to positive before you look it up. And we're looking for a p-value range, because t-tables do not give you p-values exactly, but they do give you a range of possibilities. So two-tail, n is 20, t-stat or test stat is 2.77. So a few things you have to note here. T-tables require a degree of freedom. That means that basically your degrees of freedom, often called your DF, is just your n minus 1, which in this case is 20 minus 1, which is 19. So your degrees of freedom is always equal to simply the number of things you have subtracted by 1. So you have 19 degrees of freedom. And it's also a two-tail test, which will come into play later because we're going to have to look up in the two-tail row. And my test stat is 2.777. So this is the one I want to try to get as close to as I can. So here's what I'm going to do. Go to my table. I'll have to zoom in a little bit. Find 19 degrees of freedom. Well, here's 19 degrees of freedom right there. So I'm going to look in that row. And I'm going to find as close to 2.77 as I can. So if I go, the closest I can get is right here, between these two numbers, 2.861 and 2.539. So 2.77 is somewhere between there. So I found the boundaries. I found the low and the high end. So I'm going to go up, 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 up. And I go to the area in two-tail row, and I look to the left, and I look to the right. So my p-value is somewhere between these two values here, somewhere between these two columns, the 0.01 column and the 0.02 column. So when I go to my values here, I'm going to say that my p-value is somewhere between the two numbers that I was just looking at, 0.01 and 0.02. So I go there and say it's somewhere between 0.01 and 0.02. Why? Well, again, just looking at the table here, it was smaller than this number and bigger than that number. So it was on the right side of this number and on the left side of that number, because it's somewhere in between them. So it's on the right side of 0.01 and on the left side of 0.02. So it's bigger than 0.01 but less than 0.02. I don't know exactly, but I can give that estimate the best I can. For a right tail test, again, we're not looking up the entire problem, we're just looking up the p-value, the range of p-value rather. So it's a right tail test, n is 9, 3.60. So let's go ahead and make sure we get our degrees of freedom. So our degrees of freedom in this case is 8 because it's n minus 1. And our test stat is 3.6. Okay, so let's go ahead and look at our try here. Here's 8. I want to get as close to 3.6 as I can. Well, if I go here at 3.355, well, this is a problem. We keep going smaller. 3.355 is the closest I can get. Anything past that is much less. So I'm not really between two numbers. I'm just simply right here. I'm right above 3.3, which means I'm right above 0.01. So this is where you have to kind of think a little bit and say, okay, 3.6 is above 3.55. Where is it? There it is, 3.355. Also, I should be using this column instead. I was doing the area in two-tail, which is a no-no because it's a right-tail test, so it's only one tail. So I should be using this number up here. So my apologies. Think of me as going to this number. So 3.355, I look up, and I'm above or below, however you want to call it. I'm after this number. So you have to kind of think and say, okay, how are these areas going as I go this direction? As these numbers go closer and closer and closer to 3.6, as I keep going closer and closer and closer to that value, what happens with my area? Well, 0.01, 0.05, 0.025, 0.01, 0.0005, these areas are going down or down or downer as you keep going to the left, right? They keep getting smaller and smaller and smaller and smaller and smaller. So as these numbers go up, these numbers go down. So if I'm looking for the probability range, if my 3.6 is above this number, that means its probability is below this number because 3.6 is to the right. So as I keep going to the right, they keep going down. So I would say that my p-value is going to be less than 0.005 because as you go to the left, your area gets smaller, and I'm going to be very far to the left of this number, so my area is going to be a much smaller one than 0.005. So that would be kind of how I write that one. So if you're on the edges of the table, you have to kind of think about, okay, am I going above or am I going below? Because that will kind of determine whether you're going to be PV is above a number or PV is below a number. So in this case, in terms of the direction, my number was going to the left of the table. So if I look at how the values are going, when they go to the left of the table, they're going down. So it's going to be less than 0.005. If it was on this end, and I'm going this way, like let's say my test stat was 0.6, well, that would be to the right of this number, which means it would be greater than 0.1 because as I go down this way, the values are increasing. So if it's on this side of that value, it'd be increasing past 0.10. And then lastly on this one, we have find the critical value. Okay, so this again is not asking for a full problem, just the critical value using this items here. Now, critical value is not the same as the test stat. There's no formula for it in this case. I just simply want to use this information to see if I can't get something out of it. So let's go ahead and say, okay, HO and H1, because critical values do need your hypotheses to help guide you. So HO is mu is equal to 6, and then H1 is that mu is not equal to 6. Now, why do I know it's not equal to? Well, it says the mean number of pickles on a sandwich is 6. So I'm claiming that it's equal to 6. So my alternative is that it's not, because I have to have kind of a counterclaim. I have to have a alternative to test it against almost. So I can't say greater than, because that's not all I'm testing against. I'm testing whether it's going to be greater or less, because my claim is that it's exactly 6. So if that's my claim, I could be wrong as it being too many, or I could be wrong as it being too few. So I just say that my counterclaim is that it's not equal to, so I get both ends of the stick there. The critical value needs an alpha, which in this case they told me is 0.05. And the critical value needs degrees of freedom, which in this case they tell me is 12. And I have lowercase s. So I have x bar and lowercase s, which means that this is going to be a t-table problem. And how do I know it's a t-table problem rather than like a z-table problem? Well, because if you have an average and a sample deviation, that means that you're doing a t-test. If you have the average and the sample deviation, you're doing a t-test. If you have the average and the population deviation, so if this was a sigma instead of an S, then it would be a z-table type of question. Because if you know the population deviation, there's less assumption involved, there's less variation involved, so you can use a z-table, which is a little bit more precise. For sample deviation, that's kind of like the best estimate you can get. So we use a t-table instead, which accounts for larger variations because we don't necessarily have as much information as we might have liked. So I'm going to be looking at my t-table and trying to find the critical value that matches these requirements here. 12 degrees of freedom and 0.05 in a two-tail test, because this is a two-tail because my alternative hypothesis here is not equal to. So anytime you see the not equal to, that means you're going to be using a two-tail test. So let's go to my table and see what happens. So here's 12 degrees of freedom. I'm going to look for 0.05 in my two-tail test here. So 0.05 is right there. Again, in the two-tail one, not in the one-tail, in the two-tail column. So 12, 0.05, find out where they cross, and it's right there, 2.179. And because it's a two-tail, it's going to be both positive and negative. So again, I got this by saying 0.05 is my alpha in two tails, 12 degrees of freedom is what I have. This right here is my critical value that goes with that information, 2.179 plus or minus. So 2.179 plus or minus. That's a 9 there. So again, finding critical values means you're going to be taking an alpha, taking a probability like that, and turning it into a score. So this is actually a t-score that you can then compare against your test stat and see whether you're going to accept or reject. But for this one, it just asks us to find it, so we don't have to do all that for this problem. All right, let's go to the next one here. So once again, we're basically going to do a full run through of this problem. That's what all this wording here means. They don't really give us a full detailed problem. It's mainly just listing out the values, but we can do it anyway. So the claim is that the score on a math test is 75, and we're given this information. So a few things to note is that our claim is that it's an equal to number. Our claim is that it's equal to 75. So when I write my hypotheses, HO is going to claim that the average is exactly 75, whereas H1 is going to claim that the average is not 75. Not more than, not less than, but just simply not 75, because again, it has to be a counter to the null hypothesis. And unlike before, our claim is actually the null, which doesn't happen too often, but in this case it did. So we're claiming equality. We're claiming that it is equal to 75, not that it's not equal to 75. So what we're going to do now is we're going to take all those numbers that they give us down below and try to put them into a formula. So the first thing you want to do, if you're testing an average, you're testing a mean, the first thing you need to ask yourself, do I have the sample deviation or do I have the population deviation? If you have sigma, which is the population deviation, sigma means you have a z-score table test that you're going to be doing. If you have the sample deviation, which is lowercase s, sample deviation, that means you're going to be doing a t-score test. So if we look down here, we notice that we have the sample deviation. So this is going to be a t-score or a t-table kind of deal here. This is going to be a t-table kind of test. So first thing we need to do, regardless, is still find out our test stat. So we first need to use our formula. And again, I wrote the formula back before. It's in the back of your book. I'm not going to bother rewriting it here. I'm just going to put the numbers in there. But it was x bar minus our claimed average, which was 75, over our s divided by the root of our n, which is 20. You plug that big mess in and you get 3.44. And now you want to find, well, let's first box that in. So that's our test stat. Now I want to find something to compare this against. Normally for a z-score, what I would do is I would take this number and convert it into a probability using my z-score table. So if this was a z-score, not a t-score, which it is, but if it was a z-score, I would go to my z-score table, find 3.44, I'd find those two values on the end there, and figure out what p-value intersects that, which would be like somewhere down here. But it's a t-score table instead. And again, as we said, t-score tables don't really give you exact probabilities. I can give you a range of possible probabilities, but I can't give you an exact value. So what we do is we simply find the critical value instead. We find our CV. So instead of a p-value, we're going to find the critical value because once again, it's a t-table test since there's an s involved, not a sigma. Since we only know the standard deviation of the sample, we're going to be using a t-table test instead of a z-table test. So if you don't remember, to find the critical value, what you do is you're going to take your tail, which is 0.1. You take your degrees of freedom, which in this case is 1 minus n, which would be 19. I should put 0.10 just to be certain. And you're going to take what kind of tail test it is, two-tail. And you're going to use that information to look up what score goes with this set of items here. So 19 degrees of freedom, 0.10, and a two-tail test. So here's two-tail, 0.10, there it is right there. 19 degrees of freedom, right there. So it looks to be about, kind of hard to read at the screen there, so give me a second here. 1.729 it looks like. So 1.729 is 19 degrees of freedom, and it's 0.10 in a two-tail test. So 1.729, again, is my CV. Okay. So now I want to compare my CV to my test stat. So this is my test stat. Test stat. Okay. So the way you compare this for me at least is I have to draw it out. So I'm going to draw my Humpty Dumpty graph there, and I draw my critical value first. So my critical, by the way, this is plus or minus because it's a two-tail test. A two-tail test always has two critical values, one positive, one negative for a t-table. So that's why I have to put the plus and minus there. So let me draw my Humpty Dumpty graph a little bit better because that doesn't look very bellish. Let's try it again. It's a little bit better. So we're going to plot my critical values first. So here's 1.72 or 1.73 if you're rounding. I'll just put 729. And then here's the negative counterpart, because it is a two-tailed test, so I have to account for both. So negative 1.729. This is a left tail side, so I'm going to shade to the left. This is a right tail side, so I shade to the right. And I want to find if my mean that I'm claiming, 75, is going to be accepted or rejected. So I'm going to take my test stat and figure out where it would go in this little area here. Well, 3.44 is a lot bigger than 1.7, so it's probably going to go to the right. So 3.44 is going to be somewhere in there. 3.44. And the rule of thumb is that if your test stat is in the shaded region, then you're going to reject the null hypothesis. So these shaded regions are the regions where something is so unique or so rare that is statistically significant. So what we're saying here is that it's statistically this result here, the mean score being 75 or whatever, is statistically significant of the status quo not being so. So this means that something is afoot here if you're in that shaded region. So this region, the shaded region, is where you reject HO. The non-shaded region is when you fail to reject HO. So my phrasing here, if I'm doing this on my typing here, would be I reject the null H, which instead of saying HO, I'm just going to say null H, which is the same thing because it's the null hypothesis. So I reject the null hypothesis, and because my claim was the null hypothesis itself, so I rejected the null, I claim the, not claim, but I support the alternative. Well, in this case, my claim was the null. So if I'm not claiming the null, if I'm rejecting the null, that means my data does not support my claim. So data does not support claim. Again, why does it not support? Well, because I claim the null hypothesis. This number here, my test stat, is so rare a chance to happen in this zone here that my null hypothesis probably isn't likely. So since I rejected the null hypothesis, it does not support my claim, which would have been my alternative hypothesis if I had guessed correctly. So again, that's still testing a mean, but as I said, the means have two different types of problems. One z-score problem, like percentages, and one t-table problem. A t-table problem is when you have S, or the sample deviation. A z-score problem is when you have the population deviation instead. So again, don't get those two mixed up because it's very easy to. The last type of test we did was a chi-squared test, or a chi test. And these required yet another table, which is this right here. This is a little different than the one that would be in your book, but it's still the same value. So my middle split is down here. So here's 0.9 and here's 0.1. So my middle split would be right down there to my quote-unquote left tail side and right tail side. Again, like a t-table, remember that these assume area to the right. So you have to kind of keep that in the back of your head here. Excuse me. So in this case, I just want the critical value. I don't want to test all the way through. I just want what the CV would be. So let's find that. So sigma is bigger than 30.5. So that means it's going to be a right tail test. So it's a right tail, which is going to be important to me. N is 10, which means my degrees of freedom is going to be 9. And the significance level is 0.01. So my alpha is 0.01. So let's look these up and see what we get. Right tail, 9 degrees of freedom, 0.01. All right, here's 9 degrees of freedom. And then it was 0.01, right? Not 0.10, but 0.01. So 9 degrees of freedom, 0.01. So I'm going to look at the top here. Where do I see 0.01? Right here. That's 0.01. And they look like subscripts, but it's just the way the table is notated. So this is just like our probabilities, essentially. So 0.01, that's the significance level I'm looking for. And my degrees of freedom is 9. So 9. So I look for where they cross, and it looks to be about 21.6 repeating. So my answer here would be 21.6 repeating would be my critical value. That would be the one I graph on the graph and see whether my number falls in front or behind that to figure out whether I accept or reject or fail to reject the null hypothesis. So once again, just like a t-table almost, figure out what kind of tail you're using, figure out your degrees of freedom, figure out your alpha, and then look it up. The only one that's tricky is a two-tail test. So for a two-tail test like this one, so this is a two-tail because it's a not equal to, you still get your degrees of freedom as 19, But for chi-squared, so unlike a t-chart, a chi-squared does not have a table column just for two tails. You have to do a little bit of manipulation on your own here. This one might sound like a doozy at first, but try to stick with me. So my alpha is 0.10, right? That's the total probability. That's a total chance. That's my total percentage is 0.1, right? My total threshold. If it's a two-tail test, that means half of this is on the right and half of this is on the left of my graph essentially. So half this is testing too high, half this is testing to see if it's too low. So what I'm going to do is that should be equal there by the way, alpha equals 0.1. I'm going to split this in half, divide it by 2, which gets me 0.05. And this, again, since it's a chi-squared, this is to the right. So this is my quote-unquote positive critical value. So if I'm drawing my Humpty Dumpty graph here, let's say my critical values were here and here, because again, a two-tailed test has two critical values. So let's say this was a CV and this was a CV. 0.05 means that the critical value right here has an area of 0.05 to the right of it. But for a two-tailed test, I have another critical value over here that also has 0.05 to the left. Unfortunately for chi-squareds, it's not as simple as just putting plus or minus because they're not symmetrical. So you have to do a little bit of digging here. So what you're going to look up is two things. You're going to look up the right critical value, RIGHT, the right critical value, by using the 0.05 number, 0.05, which is what we got from dividing it by 2. And you're going to look up the left critical value, because remember there's 2 and a 2-tail, left critical value, by doing 1 minus 0.05 and getting 0.95. Because that would be the area to the left of that critical value. So I'm looking for a critical value that two critical values rather, that balance these sort of ideas here. One where you have 0.05 to the right, and one where you have 0.05 to the left, or put another way, 0.95 to the right. Because if you have 0.95 to the right, that means you have 0.05 to the left. So I want to know what two values reach those conclusions. So let's go to our table here. Remember, our degrees of freedom is 19, so we'll keep that in mind. Let's do the right one first because that might be easier. So 0.05, 0.05, right here, 0.05. And I just told you, remember, but I forgot, we have a total of 19 degrees of freedom. So 19 is right there. And you figure out where they cross. So 19 degrees of freedom, 0.05 for chi-squared. We end up with 30.144 as my right one, 30.144. For my left tail test, I'm going to look for 0.95 on the top. So 0.95 would be about, that's 995, 990, 975, right there. 0.950, whoops, come on. 0.950, 19 degrees of freedom is there. We'll figure out where they cross. We get 10.117. So 0.950, 19 degrees of freedom, 10.117. So 10.117 would be my other critical value. If this was a t-test, a t-table test, all I would need to do is just put 30.114 plus or minus, because a t-table test can be negative. For a chi-squared test or a chi test, you can't get a negative score. So what you have to do is this right and left tail stuff to make sure you're looking at the right zones of your critical value. So when you're looking up a critical value for a two-tail test and a chi-square table, you want to make sure you cut the significance level in half and then do a right tail test on it and then do a left tail test on it essentially. So take 0.05 and do a right tail test and find the critical value, then 0.05 and do a left tail test, which will recommend you to subtract from 1, and then find that critical value. So basically just do the same problem twice. Once for the right and once for the left. So last one here. I apologize if my voice is going. I'm a little bit vocally fatigued here, but I'll do my best. Last one here is one final all the way through problem. So from start to finish testing a claim. In this case, the claim is about a deviation. So this is going to be a chi-squared test. And how do I know it's chi-squared? Well, because we're testing a claim about a deviation. Now, they don't give us the sample deviation. If you remember, for a chi-square test, we need the n, we need the population deviation, and we need the sample deviation. And we also need our alpha, of course. Well, they give us our alpha, 0.05. That's nice enough. But they don't directly give me my S or my N. They do say that the deviations are going to be claimed to have a deviation of less than 1.9 minutes. So that is my claim deviation. I at least have that. But half the stuff I'm missing. I don't know what my N or my S is. Well, I'm going to look at the data they give me. This right here. This will tell me what my N and my S are. So let's erase that here actually so I get more room to write. So my N in this case is going to be 1, 2, 3, 4, 5, 6. So I have 6 data points I'm looking at. If you plug these into your calculator, you can get the standard deviation quite quickly. So if you look here, you go to first turn on, you go to stat, you go to edit, and list, you type out these numbers. So 5.4, enter 1.1, enter 0.42, enter 0.73, enter 0.48, answer, and 1.10, answer. So you look here and make sure all your numbers are entered in correctly, which they seem to be are. So we go to stat, calculate one of our stats, enter, and we get that our standard deviation is this little S1 here. So 1.9142 is my sample deviation. That's the one I want. Don't pay attention to this bottom one here because again, it's just a rough estimate. You actually don't know the population deviation based on just these 6. So we're going to be using the S of X1 instead. So 1.194 would be what our calculator told us as the S. So this means that S is equal to 1.194. So 1.194, or was it 914? I forget. 914, my bad. Another little calculation error. 914, which sounds a little bit easier. 914, and then over here, 914. 914. Make sure I try to not make these mistakes too often. So now that I have all my data set, I need to write down what numbers I have and what hypotheses I'm testing. So let's write the hypotheses first. So HO, my hypothesis is that, let's see here, I'm claiming that the wait times have a deviation of less than 1.9 minutes. So my HO is going to be that the wait times is equal to 1.9 minutes in terms of deviation. And I shouldn't be using mu, I should be using sigma because we are claiming a deviation. Again, a little bit fatigued here, so I'm trying to make sure I get my numbers straight. So it's a sigma because we're testing a deviation. H1, deviation of less than 1.9. Okay, well here's my sigma, less than 1.9. So that's my claim. We'll put a little c there. And it's less than, so it's going to be a left tail. Left tail. Left tail, there we go. Hard to write with the pen, believe it or not. So first thing we do, get our test stat. So we use that chi-squared formula. Once again, very back of your study guide has the chi-squared formula in there. It's n minus 1 times s squared over sigma squared. So we're going to say n, which is 6 minus 1, times s squared, which is 1.914 squared, over sigma squared, which is 1.9 squared, which will give us 5.075 as my test stat. So that's my chi-squared score, my test stat, whatever you want to call it. I need something to compare it against. Well, chi-squareds don't do p-values that well, so we're going to go down the critical value method. So we want to find my CV. If you notice, the only time we used p-values was when we had a z-score. Well, this is a chi-squared test, so I'm not doing a z-score, I'm doing a chi-squared score. So I want to do my critical value, not my p-value method. So to find my critical value, what I need is I need my degrees of freedom. So degrees of freedom in this case is 5, because it's 1 less than n. I need my alpha, which is this case the standard 0.05. And I need the tail, so left tail. Left tail. So I'm going to combine all this information and get me a critical value. So combine all that information. Let's look at our little chart here. Now, because it's the left tail test, we're going to temporarily take alpha and make it into 1 minus 0.05, which is 0.95. Because of the left tail test, we want to make sure that we change it into 0.95 when we look it up, because remember, a chi-squared assumes that you're looking from the right, but in this case, we're clearly looking from the left. So let's go ahead and go to our table and find our chi-squared table, which is popped up here. That's good. 0.95, right there, 0.95. So that's the column we're going to look at. And we have 5 degrees of freedom, so that's going to be right there. We're going to look over, and we see 1.145. So that's going to be my critical value, 1.145. So go here, and 1.145. So again, why did I do what I do? Degrees of freedom I need to get the left-hand column. I did this 1 minus trick because, again, chi-square assumes you're going from the right, but this one is a left tail test, so we're going from the left. So I need to do 1 minus that probability in order to get the right orientation. So now I'm 0.95 to the right, which is the same as being 0.05 to the left, which is what I started with. Getting a little cotton mouth here, so I apologize if I'm slurring my words. So that's my CV. And now we can finally get to comparing. I'm just going to draw a number line here because I need to figure out, okay, whether I'm going to fail to reject or reject. So you plot your CV first. So I'll put 1.145 right here. 1.145. Draw a line up. It's a left tail test, so I'm going to shade to the left. So shaded region, rejection zone. Non-shaded region, failed to reject zone. 5.075 is going to be bigger than this number, right? So it's going to be to the right. Bigger numbers are always to the right of other values. So it's going to be somewhere like right here, 5.075. So again, test stat always is plotted last. That way you can figure out what zone it pops in. So this is in the fail to reject zone. So that's exactly what I'm going to say. So fail to reject the null hypothesis, and thus data does not support claim. So it's not support claim because my claim was the alternative. I failed to reject the null. So if I go and put my check marks here, I failed to reject the null. So that means the null won, the alternative did not. So this occurrence was not rare enough. It was not unique enough to warrant any suspicion that something might be happening. So we failed to reject the null hypothesis. Therefore, the claim that the deviation is less than 1.9 is not supported. You would need more data or a different sample to back up that claim if you're going to continue down that route of believing that. So again, I get this is kind of a heavy packed chapter, but it's just something that you have to get through for stats. Stats sometimes isn't easy, but despite it being very heavy, a lot of the stuff is very similar. The first thing you do is list out your numbers. The second thing you do is get your hypotheses. The next thing you do is get your test stat using the formulas that you're given for the quiz. So it starts out the same thing every time. Excuse me, the same thing every time. It's just once you get the critical value and the p-value stuff, it starts to differ. But most of the stuff is very consistent. So again, practice makes perfect. The more we get these under our belt, the easier and easier they come bit by bit by bit. Sorry for the long video. These problems take a little bit of time, and I'm halfway tired right now, so it might not have been the best. As always, feel free to ask me if you have any questions. Hope you enjoyed the video. Have a good day.